Multicast stays in your LAN. Multicast is almost always local network only. It does not go to the internet. It usually has TTL equals to 1. Routers normally do not forward multicast between subnets. So even if you're not browsing, you're not contacting a server online, you're just casting to a TV, discovering a printer, or streaming NDI locally, the packets still need leave your laptop through a physical network interface to reach other devices on your LAN. Why Wi-Fi is still needed? Because your Wi-Fi NIC 192.168.1x is the network interface connected to your home LAN. Is the only path to other devices like smart TVs, printers, phones, NAS, etc. is the interface that converts IP multicast to Ethernet multicast MAC. So this Wi-Fi NIC, the 192.168 we saw earlier as converge, are the only one that converts the IP multicast to an actual Ethernet multicast MAC. So even if you're just on your same LAN, you still need your Wi-Fi NIC to be able to convert that to connect to Chromecast. If you unplug Wi-Fi, your laptop has nowhere to send the frame. The multicast cannot reach other devices. Services like Chromecast, AirPlay, SSDP, MDNS, DLNA stop working. So even though the traffic never touches the internet, it still uses the Wi-Fi card as the exit point to the LAN. Analogy: think of your LAN like a house. Multicast, shouting inside your house. Router, front door. Internet, outside world. You're not going outside, but you still need to shout through a door or window connected to the room where other people are. That's the Wi-Fi interface. Why loopback doesn't help? 127.0.1 is internal only. Packets never leave your OS. No devices on the LAN will hear them. Multicast discovery won't work. So loopback cannot replace Wi-Fi for LAN multicast. So loopback is only within your OS or within the laptop. Why Hyper-V also doesn't help? The 172.17.x.x Hyper-V virtual adapter is its own virtual network, seen only by VMs and emulators, is not connected to your LAN unless bridge. So it's not connected to your Wi-Fi unless you bridge. So multicast sender stays in the VM network. It's only created for virtual networks such as emulators, such as Memo. Final answer: yes, even if you are not sending traffic to the internet, only doing LAN discovery, streaming locally, your Wi-Fi interface is still required because it is your only physical connections to the LAN, and multicast needs that to reach other devices. So you need to a local area network to be able to connect to Chromecast or smart TV, etc. So you need a network because it doesn't exist inside your laptop. It doesn't exist in indirect delivery either because it will be too unsecure. Do I need to connect my laptop and smart TV to the same Wi-Fi? Yes. If your laptop and smart TV or printer are on the same LAN, same Wi-Fi network, or same router, then they can communicate directly. They can discover each other using multicast, MDNS, SSDP, etc. They exchange multicast via layer 2 Ethernet frames. If your TV is not on the same LAN, like mobile hotspot or another router, discovery won't work automatically. Is the Wi-Fi interface the only one converting to multicast MAC address? Not exactly. Let's clarify. Your laptop converts IPv4 multicast to 01:00:5E. colon XX colon XX colon XX. IPv6 multicast 233 colon 33 colon XX colon XX. So the IPv6 format. But remember, um, 32 possible IP address could be mapped into each MAC address. So there's a confusion. That's why you need a higher level to further filter that mapping, because it's not always accurate. This logic happens in OS kernel, network stack, network card driver. The Wi-Fi interface is just the exit door. It sends the frame out on the air to the LAN. So the job is split is component, laptop OS, role, converts IP multicast to Ethernet multicast MAC. Component Wi-Fi NIC role, transmit the frame onto the LAN. So the one converting the IP multicast that you want to send to Ethernet MAC is actually your laptop OS, but the one transmitting the frame onto the LAN is the Wi-Fi NIC. Hyper-V and loopbacks aren't connected to your physical LAN, so even though they can convert it, there is nobody to receive on the other side, because to be able to communicate with those applications that can receive LAN, it needs to be connected to a local area network. But since those Hyper-V and loopback it's in their own bubble, or it's their own computer only and not connected to the LAN, therefore nobody on the other side will be able to receive it. Third, why not just use the internet to reach the TV or printer? This is a perfect question and touches deep networking concepts. Reason 1, local devices shouldn't depend on one. If your internet dies, you don't want your TV unavailable to receive screencasting, your printer unusable, your smart home office. LAN guarantees connectivity even without internet. Reason 2, bandwidth. Casting video on LAN 30 to 200 Mbps, no ISP charges, no need to route through remote servers. If this went to the cloud, laptop to internet to cloud to internet to TV, you would burn massive bandwidth. Saturate your WAN upload, introduce latency. LAN avoids all this. Reason 3, security and privacy. You don't want every screencast going to the cloud, every smart home device exposed on public internet, printing routed through external servers. LAN equals to private, secure, local. Why multicast works only on LAN? Because multicast is linked local, IPv6 FF02 scope. Routers drop multicast by default. Home ISPs don't carry multicast for customers. This is intentional to prevent multicast flooding across the world, smart TVs from talking to random devices globally, router overload. Fifth, how to bridge your Hyper-V virtual network if you wanted to. Yes, real professionals do this when they want VMs to appear on the real LAN. So you can actually bridge the loopback or the Hyper-V if you want to connect it to the LAN. Virtual machines to use the same IP range as physical devices. Containers to join the LAN directly. It works like this. In Hyper-V Manager, first in Hyper-V Manager, second, create external virtual switch. This bridges the VM switch to your Wi-Fi or Ethernet, lets VM share the same LAN 192.168.1.x, allows multicast to flow between VM and LAN. After bridging, a VM can send MDNS or SSDP discovery packets. TV, printers, NAS can respond. VMs behave like real machines on the network, but most people don't bridge Wi-Fi because Wi-Fi adapters often restrict virtualization bridging. Ethernet is more reliable for Hyper-V bridging. Enterprise setups usually bridge via wired Ethernet. Use managed switches with IGMP snooping. Do normal people do this? Home users usually no, except Docker power users, developers, pen testers, network students. Enterprise and data centers, absolutely yes. Bridge virtual switches are normal in VMware, ESX, Hyper-V, KVM, Proxmox, because VMs need to behave like normal servers. Final summary, why do you need LAN for smart TVs or printers? Because multicast discovery is local only. Internet doesn't carry multicast. LAN avoids latency, one load, and private problems. Who converts multicast? OS converts IP multicast. Ethernet multicast MAC. Wi-Fi NIC just transmit it. Why multicast doesn't work if you disconnect Wi-Fi? No interface equal nowhere to send frames. So if you have no NIC connected to a network or to a LAN, nowhere to send frames. Can Hyper-V be bridge? Yes, professionals do it to let VMs join the physical LAN. Receiving multicast diagrams. Fundamental to casting is the concept of a process joining or leaving one or more multicast groups on a given interface on a host. We use the term process to mean a program being executed by the operating system, often on behalf of a user. Membership in a multicast group on a given interface is dynamic. It changes over time as processes joins and leave groups. In addition to joining or leaving groups, additional methods are needed if a process wishes to specify sources it cares to hear from or exclude. These are required parts of any API on a host that supports multicasting. We use the qualifier interface because memberships in a group is associated with an interface. A process can join the same group on multiple interfaces, multiple groups on the same interfaces, or any combination thereof. Example, it is possible to determine what multicast groups are in use on each interface using an operating system specific commands. In Windows, the commands are part of the netsh package. For IPv6, this works as follows. For IPv4, replace IPv6 with IP. So we have netsh interface IPv6 show joins. Here, we can see how IPv6 uses several multicast addresses per interface. The first interface is a loopback local interface. The only multicast group used on it is the link local scope simple service discovery protocol SSDP multicast address. Note, SSDP is described in an expired Internet Draft GCLG99 authored by Microsoft and Hewlett-Packard. SSDP also operates on IPv4 using address 239.255.255.250 and UDP port 1900. On the other network interface, the address FF01:1 node-local all node address and FF02:1 link local all node address show joins for all nodes, and FF02:C shows the use of SSDP. The next address FF02:1:3 is for support of LLMNR, local multicast name resolution system mentioned previously and discussed in more detail in chapter 11. Finally, the address FF02:1:FFDC:FC85 is the solicited node multicast address for this node, used by IPv6 ND. Recall that in IPv6, determining neighbors MAC address is accomplished using multicast ICMPv6 ND messages, as opposed to the ARP mechanism used in IPv4. On Linux, the netstat command displays the IP group membership. Netstat-gn. The output from this command includes the join information for multiple interfaces and for both IPv4 and IPv6. In this case, we see 224.0.0.1 all hosts on both the Ethernet interface ETH1 as well as the loopback interface LO. We can also see the link local scope, all nodes binding for each interface. Finally, the solicited node address ff02 1 ff2a 1988. First, the core concept. A multicast group is like a radio channel. If your process wants to receive messages from that group, it must tune in, join. If it leaves, it stops receiving. A computer has multiple interfaces. Examples on your laptop: Wi-Fi, Ethernet, even if unplugged, loopback 127.0.0.1, Hyper-V virtual adapters. Each interface can have different multicast membership. So joining a group is not global. It's per interface. That's the first big idea. So since you could have multiple interface, joining a group is not global. It's per interface. Why do we need a table? Because your computer might join many groups on multiple interfaces at different times. So you could have multiple groups at multiple interfaces at different times. So you need to have a table to keep track of it. So the OS gives a table of which interface is joined to which multicast groups right now. Otherwise, the OS wouldn't know where to deliver incoming multicast packets. You couldn't debug group membership. Applications wouldn't know what they're listening to. This is like you tune your radio to channel 95.1 on radio 1, channel 88.3 on radio 2. Your computer needs to remember that mapping. What NetSH interface IPv6 show joins shows? It shows for each network interface which multicast group it is listening to right now. Example, interface 5. Palagay na lang po dyan. Palagay na lang po. Ay, malaki po ba? Opo, palagay na lang po dyan, sir. Palagay na lang po dyan. Opo. Example, interface 5. So what in NetSH interface IPv6 show joins shows? It shows for each network interface which multicast group it is listening to right now. Example, interface 5 Wi-Fi. We have ff02 FB, ff02 1, ff02 C, ff02 1 ffxx xxxx. If each of these multicast addresses has a purpose. Why do you see many multicast addresses? Because Windows and Linux, Mac routers automatically join multiple multicast groups on every interface for system functionality. For example, multicast address ff02 1 meaning all nodes on this link. So that is automatic through operating system. They join this automatically. Then ff02 FB MDNS for discovery of services like printers, smart TVs. Then ff02 FFXX FXXXX solicited node IPv6 replacement for ARP. Then ff02 C meaning SSDP UPnP discovery. You didn't manually join these. The OS did because name resolution, neighbor discovery, auto configuration, device discovery all rely on multicast. So the table is simply a list of all multicast groups currently required by system services and applications. So why is it confusing? Because it uses precise formal networking language. It jumps between IPv4, IPv6, API behaviors, and OS commands. It assumes you already understand multicast behavior. So let's unpack the passage, breaking down each sentence. Membership. So what does it mean by membership in a multicast group is dynamic, meaning a process can join or leave the group at runtime. So remember, the runtime is where you allocate some time slice to a process in OS. In the previous video, it is not fixed at boot. Same as you can start listening to a radio channel whenever you want. Membership is associated with an interface. This is key. If your laptop has Wi-Fi interface number 1, Ethernet interface number 2, a program can join ff02 FB MDNS only on Wi-Fi. The OS must track which interface is listening to which group. That's why table exists. A process may join the same group on multiple interfaces. Yes, join MDNS on Wi-Fi, join MDNS on Ethernet. These are separate memberships. You can send to a multicast group without joining it. This is important. Joining is needed for receiving. Sending only requires you to send to the multicast address. So you don't need to join to that multicast or to that multicast group if you are a sender. Example, ping ff02 1 sent to everyone on the link. You don't have to join ff02 1 to do this. The example, interface 8 local area connection. We have ff01 1 2, which is node local all nodes, ff02 1 which is link local all nodes, ff02 C SSDV, ff02 1 3 LL MNR name resolution, ff02 1 FFDC FC85 solicited node for my own IP. So this tells you this network interface is currently listening to link local all host announcements, SSDP, UPnP, name resolution, NIVOR, discovery traffic. Nothing mystical, just system services subscribing to necessary radio channels. Why do you see the loopback interface in the table? Because the loopback adapter also support multicast locally. It's useful for processes on the same machine talking to each other. No NIC involved. So what's the big picture? When multicast arrives on an interface, OS looks at the multicast MAC. It maps it to a multicast IP. So that multicast MAC, it will be mapped to multicast IP because again, there could be multiple multicast IP. It looks in the membership table to make sure that that MAC is actually for this multicast IP. If the interface is subscribed, it is delivered to application, if not wrapped silently. This table is how the OS know which packets matter. Final analogy, think of an apartment building. Each room interface has its own mailbox. Tenants' applications subscribe to a particular newsletter, multicast groups. The mailroom OS must know which room wants which newsletter. Otherwise, mails get lost. Wrong room gets the wrong delivery. No one can debug anything. Host address filtering. To understand how the operating system processes receive multicast datagrams for multicast groups that programs have joined, recall from chapter 3 that filtering takes place on each host network interface card (NIC) each time a frame is presented to it, i.e. by a bridge or switch, for possible reception. Figure 9.5 indicates how this occurs. Figure 9.5, each layer implements filtering on some portion of the received message. MAC address filtering can take place in either software or hardware. Cheaper NICs tend to impose a larger processing burden on software because they perform fewer functions in the hardware. In a typical switch Ethernet environment, broadcast and multicast frames are replicated on all segments within a VLAN, along a spanning tree formed among the switches. Such frames are delivered to the NIC on each host, which checks the correctness of the frame using CRC and makes a decision about whether to receive the frame and deliver it to the device driver and network stock. So it first being checked by the CRC or in the layer 2 level before it checks through the layer 3 such as the driver and the layer 4 which is the network stock, the TCP/IP. Normally, the NIC receive only those frames whose destination address is either the hardware address of the interface or the broadcast address. However, when multiple frames are involved, the situation is somewhat more complicated. NICs tend to come in two varieties. One type perform filtering based on the hash values of the multicast hardware addresses in which the host software has expressed interest, which means that some unwanted frames can always get through because of hash collisions. So that unwanted frame is further checked in the layer 3 level. So that's actually what we call hash collisions. The other type listens for a finite table of multicast addresses, meaning that if the host needs to receive frames destined for more multicast addresses than can fit the table, the NIC is put into multicast promiscuous mode, in which case all multicast traffic is given to the host software. Hence, both types of interfaces require that the device driver or higher layer software perform checking that the received frame is really wanted, even if the interface performs perfect multicast filtering based on a 48-bit hardware address, because the mapping from a multicast IPv4 IPv6 address to a 48-bit hardware address is not unique. Filtering is still required. So because you have 32, you could have 32 layer 3 mapped to 1 layer 2 or MAC address. For NICs that support a multi-entry address table, the destination address on each received frame is compared against this table. And if the address is found in the table, the frame is received and processed by the device driver. So if it exists in the table, it will be processed by, that's the only time it will be processed by the device driver. The entries of this table are managed by the device driver software in combination with other layers of the protocol stack, such as the IPv4 and IPv6 implementation. Another method, this type of filtering, is to apply a hash function to the destination address, forming an index into smaller binary vector. So these are less accurate, but if you have small memory in your NIC, which is some NIC is burned that way, therefore you will have to accept this for now. When the index entry in the vector contains 1 bit, the corresponding address is deemed to be acceptable and the frame is processed further. This approach can save memory on the NIC, but because of collisions in the hash functions, some frames may be considered unmissable when they should not be. This is not a fatal problem, however, because higher levels of the stack also perform filtering and no frames are ever discarded when they should not have been, i.e. there are no false negatives, but there may be false positives. Once the NIC hardware has verified a frame as acceptable, i.e. the CRC is correct, any VLAN tags match, and the destination MAC address matches an address entry in one or more of the NIC's tables, the frame is passed to the device driver where additional filtering is performed. First, the frame type must specify a protocol that is supported, like IPv4, IPv6, ARP, etc. So there's also some layer that checks if it matches this specified protocol. If it didn't, it will reject that to that part of its layer. Second, additional multicast filtering may be performed to check whether the host belongs to the address multicast group indicated by the destination IP address. This is necessary for NICs that may generate false positives. The device driver then passes the frame to the next layer, such as IP. The frame types specify an IP datagram. IP performs more filtering based on the source and destination IP addresses and passes the datagram up to the next layer, such as TCP or UDP, if all is well. Each time UDP receives a datagram from IP, it performs filtering based on the destination port number and sometimes the source port number too. If no process is currently using the destination port number, the datagram is discarded and an ICMPv4, ICMPv6 port unreachable message is normally generated. TCP performs similar filtering based on its port numbers. If the UDP datagram has a checksum error, UDP silently discards it. One of the primary motivations behind the development of the multicast addressing feature was to avoid overhead broadcasting. Consider an application that is designed to use UDP broadcasts. If there are 50 hosts on the network or VLAN but only 20 are participating in the application, every time one of the 20 sends a UDP broadcast, the other 30 non-participating hosts have to process the broadcast all the way up through the UDP layer before the UDP datagram is discarded. The UDP datagram is discarded by these 30 hosts because the destination port number is not in use. The intent of multicasting is to reduce this load on hosts with no interest in the application. With multicasting, a host specifically joins one or more multicast groups. If possible, the NIC is told which multicast groups the host belongs to, and only those multicast frames associated with the IP layer multicast groups are allowed through filter in the INC. All this machinery offer less overhead imposed on the host in exchange for additional complexity in managing multicast addresses and group memberships.